Thank you very much, and good morning to everyone in the room. Sorry for not being there today in presence. As you mentioned, I'm chairing the Fairmont network, and this network is an important network in Europe, trying to harmonize modeling practices in support to the Air Quality Directive. And within this network, we have one specific working group on source apportionment. And what I will present today, before Enrico takes over, is a little bit a summary of what we are currently discussing and what we have been providing in terms of information regarding source apportionment inside this network. So next slide, please, Enrico. And to put this first in the context, we need to define what is source apportionment. So what we have here is a very, very general definition of source apportionment. So it is a technique used to relate emissions from various pollution sources to air pollution concentrations at a given location and for a given time period. Of course, this is, as I said, a very general description and definition, which allows for a lot of methods and a lot of different techniques to be applied to fulfill this definition. So next slide, please. What we have been trying to define and discuss during many years now in this in the context of this Fairmont network is very basic questions related to the use of source apportionments to support air quality management. And basically, in general, what we see in terms of source apportionment is a pie chart with different sources explaining different contribution to the concentration at a certain location. But this is a very simple representation, and are results always possible to put in terms of a pie chart? Is that always possible? Is a simple representation always simple to interpret? It's not enough to have a simple representation. Then we need to interpret and to provide simple information to the policymakers. And also, what is the purpose? Why do we use this source apportion for? So these seem very basic questions, but we have discovered they hide a lot of complexities, and it's not always to answer them very precisely and simply. Next slide, please. The first thing we tried to do was to decompose the source apportionment concept in different elements to help us a little bit organize and answer these questions that I mentioned before. And we have identified basically four blocks that define source apportionment. The first one, of course, is defining the source in terms of their spatial and temporal characteristics. We need also to define the receptor, so the place where we will look at the concentration and where we want to assess the impact of these sources. Then, of course, we have all these processes between the source and the receptor, and we need a technique to manage these, to capture these processes. And this is what is mentioned here by the pathway, and this is captured through the source apportionment method itself. And then, of course, the basic also information that we need to take into account is which indicator do we look at. And I will go through these four elements and show that the choice of these and the definition of these elements determines very much the results that we will have at the end. Next, please. I will start now with the method. And next, please. And for the method, we have different type of methods. We have identified four on which we have been working in this network. The first one on the top left is called impacts. And I have listed a series of modeling tools that apply this type of techniques in current days. And the impacts is simply you take a base case with your model and then you switch off or you reduce a source within the model, and then you look at the difference between the two, and this provides you an information about the role or the impact or the contribution of this source. Then we have on the top right the receptor contributions. This is basically a technique which is working more with the measurement, closer to the measurement side. There, the principle is to identify from the source itself to have some kind of ID card, what we call a fingerprint of what this source is emitting. So this can be taken at the chimney, or this can be taken from information from the factory or whatever. And once we know what is being emitted, then we can recognize as traces what then reaches the receptor at a later stage. Then we have on the bottom left the increments, and the principle is very simple. It consists in taking two locations, one that is influenced by the source and the other one which is not influenced by the source. And by making the difference between the two, we estimate the impact of this source. Finally, on the top right, sorry, the tagging contributions. This is also an entirely modeling approach where we tag, so we put a label on each of the source and we follow them through the different processes, physical or chemical, in the model itself, and then this allows to recognize what reaches the receptor at a later stage. So all these techniques exist, and one of the work within Fairmode was to compare them and to try to understand a little bit the limitations and the strengths of each method and how and when to use each of these methods. Next slide, please. And one of the results of this work, if we put all these methods on the y-axis and we on the x-axis look at different type of sources, the sources which can be considered relatively simple, which for example emit only primary PM component which don't react in the atmosphere, so we can recognize them from the source to the receptor. They don't follow any reaction or transformation, to more complex sources where we would have like secondary precursors that would transform in the atmosphere. So if we look at this and if we look only at the simple sources, then the situation is very easy to interpret. Next slide, please, Enrico. Then every method gives the same results. But of course, we cover, if we have a very complex mixture of sources, we cover only part of the pie chart. So this is not a full solution. If we want to cover everything, next please, then we see that for the secondary and more complex sources, then the responses are relatively different or quite different. And next, if we sum up, of course, to get the final pie chart, then we see that the results would differ. This is very theoretical, of course, but what we see is that in practice, the differences are quite large. Next slide, please. And in fact, the differences are mostly conceptual. This is really at the basis of the method. So we expect that these differences will be quite significant because the method itself is different. So of course, the difference can come from many different aspects. Next, please. These can come from the input data that you put in your model. This can come from the way you characterize the chemistry and the physics within your model, or this can come from the source apportionment formulation. All these will lead to differences, but even next, please, even if you use a perfect model with perfect input data, we would still have large differences at the end, because this is really a conceptual issue. And in fact, these methods are really designed to answer different questions. Next, please. And this has been put in literature, as you can see here. Next. So now, just looking at the different blocks of what I mentioned that constitute the source apportionment method, I think it's interesting also to, and this is part of the work that we also did within Fairmode, to inform on what, or to provide information on what are these different elements, to provide metadata information that helps interpret the final results. And this is really important because in many cases, source apportionment results are provided without this information, and it's very difficult to make an interpretation of these results. Just to illustrate this, in terms of the source, so we looked at the method. In terms of the source, and you have an example here, it's extremely important, for example, to define what is the source geographically. And here you get the impact of the city on its own pollution for two cities in Paris and London, which are defined according to different geographical areas, going to the city core to a more extended area in blue. And you can see that the results, which are provided on the right side then, show the impact of the city on its pollution can go from 70% to 30%, depending on what the area is chosen for the source definition. And if we go now to the receptor, next, it's also important to define very well what the receptor will be. If we take one single point in the city, or if we average the results over the whole city, we would get a factor 2 difference. And this is what illustrated in the plot below, where you can see this factor 2 appearing depending on how you define the receptor. And finally, the indicator, next. If we want to address the question of how much is the pollution, is a city influencing its own pollution, of course, we need also to define the indicator. And this is just to illustrate it, an example where we have made some simulation to test the impact of different indicators, NO2, PM2.5, and ozone. Again, with the same question, how much of the pollution in terms of these 3 indicators is generated by the city itself? And what you can see on the left for NO2, it's rather clear that all of the pollution, or most of the pollution, is coming from a local origin. This is the violet part, which goes almost to the edge, which is 100%. And if you look at the difference with the European, if you switch off all the emissions in Europe, so this is the European contribution to the pollution in the city, then it's of course 100% for NO2. For PM2.5, the situation is more mixed in the middle. You see that within a city, if you reduce emissions within the city, so the contribution of the impact of the city on its pollution is around 50% in most cases. And if you look at the contribution from Europe emissions, then you would reach almost 100%. While for ozone on the right side, then you can see that the contribution of ozone, of the city on ozone concentration, is very limited locally. And even if we look at the European contribution, this doesn't explain or explains only half of the ozone peaks that are monitored in the city. So again, this is to illustrate the point that meta information is really helpful to support the source apportionment. Next, please. So just my last slide before leaving the floor to Enrico. This is the structure of FAIR-MODE. As I mentioned, we have one group. This is working group 1, dealing with source apportionment. Next, and one of the key output of this group has been this guidance document, which is an online and living document because it's updated regularly. And next, please. This document includes, well, at first it covers particulate matter and NO2. It really focuses on air quality management, and it explains conceptually why methods lead to different results. Then it assesses also whether methods can be used in combination, so using the strengths and limitations of each method to be used in combinations. And we include recommendations on which method to use for which purpose. And finally, this is the last point I mentioned. It's important to have metadata information associated to source apportionment, and this is also one of the key information in the e-reporting system, which we try to support with our work there. Thanks for your attention, and then I leave the floor to continue to Enrico.
Okay, thank you, and good morning. Okay, so the part that I will present now is more, if you want, an implementation of all the concepts that Philippe has just described. And particularly, I will focus on this Sherpa tool and model that we developed since few years at GRC, and we use for testing of source apportionment. So the idea of the tool came because we wanted to create something to support the design of air quality plans. And in particular, we wanted to address this question that you see on the slide. So to help policymakers to understand if a pollution in a given city comes from local or external sources, which are the human activities and pollutant emission that should be tackled first. So should they work more on the agricultural sector, transport sector, and so on, and also how to possibly coordinate with the surrounding regions. So those were the questions that helped to develop the Sherpa tool. And what we did in a very simplistic way was to start from the kind of real chemical physical reaction that happen in the atmosphere when anthropogenic emission enter the atmosphere. So this is kind of what you see on the left side is a bit the description of what happens in terms of emission, dispersion, transformation, and goes from sources to impacts. And so usually to describe all this complexity and so to help in the design of plans, what you do is to use state-of-the-art air quality models that need a lot of technical knowledge and a lot of detailed input to work in terms of meteorology, emission, boundary condition, and allow to test the impact of policies. What we did was to simplify this air quality model and to build this Sherpa that is, well, trying to mimic the full air quality model in an approximated way, so losing some of the detail that are in the full model, but try to represent the main and key phenomenon that are interested for the design of air quality plans. And basically, if you then are interested, we can give you more detail, but in the literature we published all the, yes, kind of papers dealing with the methodological concept. But in very broad terms, what we do is to find a function that link the change in emission that you will have on your domain to change in concentration and impacts. And we regularly try to validate the model. So this is an example of what we did a few years ago, focusing on a couple of countries, on different regional and local domains that are defined by these empty and full boxes, squares that you see here on the left side. And on the right side, is the validation that we do. So we try always to compare on the x-axis, the air quality model per cell, the change in concentration, and on the y-axis, what you get with the source receptor. And usually what you try to do is to be very close to the bisecting line. So you see here different tests that we did on the European scale, national, regional, and local. So we developed this tool. I will give you at the end of the presentation also a link where you can access the online Sherpa version that has been recently released in November last year. But also November last year, we published our Urban PM2.5 Atlas. And this is a report that tried to address the source allocation that Philippe was mentioning using the Sherpa tool. It's an analysis that we do it every 2 years, and you find here the link. We focus usually on 150 cities, and we look at the sources contributing to pollution there. So if I now take the kind of schema that Philippe was mentioning about defining the meta information that you use for source allocation in terms of indicator, receptor, methodology, and source, I will explain you quickly how we implemented that general schema. So what we did was to, in terms of methodology, to use a brute force methodology. So as I said, we are mimicking a full air quality model with a simplified one, Sherpa. And the basic information, well, is that we are using emission for the base case in 2019, including condensable, and this is the CAMS version 6.1 that we're using. And for the meteo, the ECNWF estimation, and the spatial resolution that you see here is 0.1 times 0.05, that means around 6 kilometers. So we have a grid covering the whole Europe at 6 kilometer resolution. Then also, okay, I said now about the methodology, but you can also define all the other meta information that are required to understand the tool. So what we are focusing on is in terms of indicator, the yearly average PM2.5. In terms of receptor, for each city, we are taking the point of the city where there is the highest PM2.5 concentration. So the receptor is 1 point. And for the sources, we are playing with both sectoral and geographical sources. So we are considering the impact of reduction at the city core, commuting zone, country, and for the whole Europe plus UK, Norway, and Switzerland. And in terms of sector, we have an aggregation of the original Sherpa sector. So we focus on transport, residential, industrial, agriculture, shipping, nature, and others. And so based on all this meta information, what we do is to perform an analysis that with a Sherpa tool that can be then shown in two different ways. Or we can look at all the cities together, but then we are bounded to look at one source in terms of sector or spatial. So at a time, you can only look at one dimension, or you can focus on one city and look at all the sources together. And I will show you an example of what you find in the report in terms of overview maps and city fish. For the overview maps, you see here an example. So what we do is to focus on the 150 cities, but on the land version, there is now more than 700 cities. And what you can say is how much of the pollution in that city depend on emission at the greater city level. So you see there are cases, Madrid, Paris, and others, where really the policies at the city scale can do a lot for the pollution that you see there. In other cases, there is a lot of transboundary, for example, so the contribution will be lower in terms of greater city contribution. And on the right side, you see an example of sectoral contribution, and there it's the road transport. And again, it will depend where you are. There are cases where the road transport is contributing up to 25%, or cases where the road transport contribution to PM 2.5 concentration is much lower. And indeed, it depends a lot on where you are. And I think that is much more visible when you look at the city fish. And as I said, we produce now more than 700 of these city fish, and I will focus on this example of Brussels to explain you how to read these city fish. So what we try to do is to follow, as I said, to report all the meta information that are required to interpret the results. So here you see the receptor point, which is this green point in the center of the city. And then there is the definition of a city core and commuting zone. So the greater city is the two things together, city core and commuting zone. And these are then reflected in the main graph that you see below, but I will come in a minute. Then what we show is also the situation in terms of observation. And what you see here is the WHO guideline for PM 2.5 and PM 10 in red. And then all the points represent all the stations that are available for the city. And in this case, well, there is only one station here below the 15 microgram for PM 10. All the other for PM 10 and for PM 2.5 are above the WHO guideline. Then this is the key result. It's really the spatial and sectoral allocation. And you can read this in this way. So it's taken 100% of the PM 2.5 yearly average concentration. You can say that around 25% for this city come from the transport sector, another 20% is from industrial emission, and then you see the other contribution, agriculture, residential, and so on. And this is in total, but then you can also split the same sector contribution in terms of geographical sources. And so you can see what can be done at the core city, thanks to core city emission reduction, what can be achieved if you sum up also the commuting zone reduction, and then so on, going on with the rest of the country and transboundary. And the last thing is also, for transparency, we show the emission that are used. So these are the emission that goes in input to the whole system that come from camps, as I said. And you can see both the city emission and the greater city emission in different colors, and also the different precursors that are input of the model with the sector again, agriculture and transport, shipping, and so on. So what we concluded from the analysis that we did, so I showed you the example of one city, but then if we look at all the cities and we try to derive some general conclusion, I think what we can say is that for many cities, local action at urban scale are an effective mean of improving PM 2.5 concentration. But then the target sector and scale really depend a lot on the city. So everything here is really city specific. Then we also found a couple of signals And I think in terms of sector, we saw that residential heating is one of the sectors that should be tackled, that will have a clear benefit, and also another one that would benefit a lot PM2.5 concentration and will reduce the concentration would be action at the agricultural sector. Also because those are really tackling part of the secondary pollution that goes around in Europe. And also we did in the report test on the NEC directive, and we stress again that the fulfillment of the NEC directive, in particular on the ammonia commitment, would bring a tangible benefit to air quality in EU cities. So as I said, this model, okay, you saw the link to the report before, but also you see now the link to the model itself, so the Sherpa model. And if you go there, you can play with your own scenario in case you're interested, but also you can access the city fish for the remaining 600 cities, because in total we have around 750 now. And the only thing you need to access the tool is a EU login, and for the rest you can freely use it. And this is the landing page when you enter into the tool. And that's it. Thank you.